Okay, logarithmic differentiation is where we can use log properties to simplify the log function first, and then we can differentiate each of the terms. So let me give you a simple example. If you had y equals the natural log of x cubed times x minus 5 to the fourth power, well, remember, you can write this as the natural log of x cubed plus the natural log of x minus 5 to the fourth using your sum rule for log properties, and then the power rule, you can write each of these, you can bring the power down, so this would be 3 natural log of x for the first term and 4 times natural log of x minus 5 for the last term. Now, I have done no differentiation here, so don't think I haven't taken the derivative. All I did was rewrite the problem in simpler terms. So I just rewrote the function in simpler terms. Now, if I want to take the derivative of these functions, well, I'd have to take the derivative of 3 natural log of x first. Well, that's going to be 3 times the derivative of natural log of x, which is 1 over x. And then if I want to take the derivative of 4 natural log of x minus 5, well, that's going to be 4 times the derivative of natural log of x minus 5, which would be just 1 over x minus 5, because the derivative of x minus 5 is 1, so the chain rule doesn't really apply here. And then if you simplify that, you'll get 3 over x plus 4 over x minus 5. And so that was much easier than applying the log rule to this function. It was easier to apply the log rule to the simplified function and to get the derivative. Now here's one that's a little more complicated, but just trust me here, if you go through your log properties, you can actually write this as 2 natural log of x plus 3 natural log of x plus 1 minus 1/2 natural log of x plus 3. So go ahead and break that up with log properties and make sure you can get the same thing I got here. Now, again, taking the derivative of this, I get the derivative, I get 2 times the derivative of natural log of x, which is just 2 over x, plus 3 times the derivative of natural log of x plus 1, which is just 3 over x plus 1, and then minus 1/2 times the derivative of this. Well, the derivative of this is 1 over x plus 3, so I get minus 1/2 times, minus 1/2 times 1 over x plus 3, and so that gives me minus 1 over 2 times x plus 3. So that's the reason you can do logarithmic differentiation, is it makes it easier to find the derivative. Now you can also implicitly differentiate log expressions. Like here I have the natural log of y plus 5x equals 30. Well, the natural log of y, if I want to take the derivative of that with respect to x, well, remember, y is a function of x, so I have to apply the chain rule. So the derivative of natural log of u, remember, is 1 over u times u prime, so the derivative of natural log of y would be the same thing, 1 over y times y prime. Now the derivative of 5x with respect to x is just 5, and the derivative of 30 with respect to x is 0. And then I can solve this for y prime by subtracting 5 from both sides and getting 1 over y times y prime equals negative 5, and then multiplying both sides by y to get y prime equals negative 5y. Here's one a little more complicated. You have natural log of x squared y minus 1 equals 2x minus 3y. Well, to take the natural log of x squared y minus 1, now this is the natural log of this entire argument, x squared y minus 1. Well, what you have to do is you have to do 1 over x squared y minus 1, then times the derivative of x squared y minus 1. And we'll return to that in a minute. On the other side, the derivative of 2x is just simply 2, and the derivative of minus 3y would just be minus 3y prime. Now, let's return to this right here. To get this derivative, well, the 1, we know the derivative of 1 is 0, so that's not going to affect us. But to get the derivative of x squared y, we got to use the product rule. So the product rule would be x squared times y prime plus y times the derivative of x squared, which would give me 2xy. So I would get this here. Now, what I'm going to do next is I'm going to multiply both sides by x squared minus 1. Okay, so I think I said x squared minus 1, but it's x squared y minus 1. So I'm going to multiply both sides by x squared y minus 1 so I can eliminate this denominator. So if I do that on this side, the denominator will just cancel with this factor. And then over here I'll have 2 minus 3y prime times x squared y minus 1. Well, over here I can FOIL, so let's just go ahead and let you do the algebra on that. So if I FOIL that, I'll get 2x squared y minus 2 minus 3x squared y prime plus 3y prime. And then over here I still have these two terms, x squared y prime plus 2xy. Well, notice that I have x squared with a y, I have a y prime with this term, I have a y prime with this term, and I have a y prime with this term. So I want to get those three terms to the left. So if I move this term over, it changes to positive. If I move this term over, it changes to negative. And then I'm going to move the 2xy to the other side, and it changes to negative. Well, now I can factor out the y prime out of these three terms, and I get y prime times x squared plus 3x squared y minus 3. And then to get the final answer for y prime, just divide this factor into the factor on the right, and you'll get this expression as your final answer. Okay, so we might have the chain rule multiple times. Let's look at this. This is sine of where the argument is actually natural log of xy. So I have to take the derivative of sine of something equals the derivative of 2x. Well, the derivative of 2x with respect to x, that's the easy part. That's 2. But the derivative of sine u, where this is u, all of this is u, so the derivative of sine u is what? It's actually cosine u, so it would be cosine of that log expression times the derivative of that log expression. Remember, cosine u times the derivative of u. Okay, well now let's figure out how do I take the derivative of natural log of xy. Well, the derivative of natural log of u is 1 over u times the derivative of u. Well, that would be 1 over xy times the derivative of xy. And the derivative of xy is just xy prime plus y. And then what I did next is I multiplied both sides of this equation by xy. So when I multiplied the left by xy, it's just going to cancel the xy. And when I multiply the right by xy, I'm going to get 2xy. Well, now I can distribute the cosine of natural log of xy through these two terms, and I get, let's see, if I multiply it by xy prime, I get x times the cosine of natural log of xy times y prime, and then plus y times the cosine of natural log of xy. And over here I just get 2xy. Now I can subtract this term from the left, and that way I only have the term with the y prime left on the left side, and then divide this factor right here into the right hand side to get your final answer. Now I went ahead and showed you a picture of this weird little critter. If you were to graph this function, you get kind of a strange looking critter. Notice you get a piece here, a piece here, you get this funny looking piece over here, and you also get a piece down here. So it is definitely a strange character, but that's what the function looks like. Now we can analyze a log function, so let me take y equals x squared natural log of x, and let's find some derivatives. Okay, you can actually go through the product rule here and then simplify it to get to this step, and then you can factor an x out to get to this step. Well, if you set x equal to 0, you get 0, but 0 is not in the domain of this function. So we have to set 1 plus 2 natural log of x equal to 0 and to get the critical. So here you can look at this yourself. This is how I actually solved for x. I set 1 plus 2 natural log of x equal to 0, and I got natural log of x is equal to negative 1/2, and then when you write it exponential form, you get x equal e to the negative 1/2. And that's approximately 0.61. Now, so I'm going to break the number line at e to the, so this vertical line represents e to the negative 1/2. And I picked a number to the left of e to the negative 1/2, which was 0.5, since I know e to the negative 1/2 is about 0.6. So I plugged 0.5 into the derivative up here, And when I plug 0.5 into the derivative, it gave me a negative, so that tells me the function is decreasing on that interval. And then if I pick a number to the right of e to the negative 1/2, 1 is certainly to the right of it, so I plugged 1 into the derivative and evaluated it, and I got a positive number, so the function must be increasing on that interval. Now notice over here I started at 0 instead of negative infinity, because remember, the domain of this function, since it has a log, has to be positive real numbers. Okay, so now using the first derivative test, that tells me that I get a relative minimum at e to the negative 1/2, and the y value would be f of e to the negative 1/2, and if you plug that back into the function, you get that the y value is negative 1 over 2e. Now, the second derivative, you can go through the process of getting the second derivative here, but I'll let you do that. But let me show you. I got 3 plus 2 natural log of x, and then I set that equal to 0 to look for critical points, and I got natural log of x is equal to negative 3/2, which is equivalent to x equal e to the negative 3/2, which is about 0.22. So now right here I break the line at e to the negative 3/2. I pick a number to the left of e to the negative 3/2, which is 0.1, and when I plug that in to the derivative, I got a negative, so that function must be concave down on that interval. And then when I picked a number to the right of e to the negative 3/2, I can still use 1. So when I plug 1 in, the second derivative is positive, so the function must be concave up on that interval. So since the concavity changes at that point is actually a point of inflection, and if you plug the e to the negative 3/2 back into the function and simplify, you get negative 3 over 2e cubed. And I went ahead and gave you the approximation of that point by using a calculator. So here's the graph. There's that relative minimum that I got up here, that relative minimum. And then I got a point of inflection right here, and that point of inflection was this point that I got here. So it's concave down to this point, and then it's concave up the rest of the way. And of course it's decreasing from 0 to this point, and then it's increasing from that point onward. Okay, freeze the video and analyze this function and answer the questions in this table here, and then sketch the graph. And you can do that, and then when you're finished you can restart the video. Well, the derivative of log of x with another base is actually 1 over natural log of that base times 1 over x. So if I wanted the derivative of log of x base 2, I would just have 1 over natural log of 2 times 1 over x, which is 1 over x natural log of 2. And then if I had log of a function of x base a, then that's going to be 1 over the natural log of x times 1 over u times u prime. So if I want the derivative of log of 1 minus x squared base 5, then that's going to be 1 over natural log of 5, so there's the natural log of 5, times 1 over u, which would be 1 over 1 minus x squared, the square got left off there, and then times the derivative of 1 minus x squared, which is minus 2x. Okay, freeze the video and read this paragraph here. And then when you're done, go ahead and restart the video for the last problem in this section. Okay, so if I want to take the derivative of a function to a function, what I'm going to do is take the natural log of both sides first. Then on the right hand side I can use log properties to simplify it. And then I'm going to apply the derivative operator to both sides. And the derivative of natural log of y is 1 over y prime. This I have to use the product rule, so I'll get x times the derivative of the natural log, which is 1 over 1 plus x, then the natural log times the derivative of x, which is 1. Well, since I want to solve for y prime, I'm going to multiply both sides by y, so I'll get y prime equals y times that on the right. And then the last thing, you might think, well, I have to leave it like this, but actually remember in the beginning you knew what y was. Y is 1 plus x to the x. So you can replace y with 1 plus x to the x to get your final answer. Now, certainly you don't want to use any other rules on this or you'll get it wrong. When you have a function raised to a function and you want the derivative, this is the process that must be followed.